This is the 6th video on the Riemann integral, and for the remaining videos we're going to look at examples. So we're actually going to integrate functions. And so what we learned in the last video is that a continuous function on a closed interval is integrable on that interval, and so we can calculate the integral. The other thing that we looked at was how to do that choosing the right endpoint of the interval as our x sub I star and chopping the interval into equal subintervals of equal length of length b minus a divided by n. So this is the formula we're going to use to calculate these integrals. So in this particular example, a is -3 and b is equal to 1. And so the length of our interval is 1 minus -3, which is 4. And so we have f of, here's our a, -3, plus b minus a is equal to 4. So this is -3 plus 4i over n times 4 divided by n. This is the reason we want to use, one of the reasons we want to use this definition is now we can use our summation formulas, so what we know about summing and what we know about limits. So now we just have a limit of things defined in terms of I and n. So f of -3 plus 4i divided by n, we substitute that into our function. So this is our x sub I star. So we substitute -3 plus 4i divided by n into our function. So we have 2 times x plus 1. That's substituting that into our function. And then b minus a divided by n, so we have 4 divided by n. So now we simplify this algebraically. So take the thing in the square bracket, that is equal to 8i divided by n minus 5. So that simplified nicely. We'll distribute the 4 over n through this term. So we have 32i divided by n squared minus 20 divided by n. Now we're going to simplify this algebraically some. Remember that when we take our summations, one of our summation formulas that we learned, or our summation facts that we learned in the previous chapter, is if you sum over a sum, you can break that up. And that's simply because addition is associative and commutative. All we're doing with this step to this step is saying we can add things in any order we want. We can factor constants outside of the summation sign. So we have our 32 divided by n squared, we factored outside of here. And you're thinking, well, n's not a constant. Well, it is and it isn't. It's not a constant when you're calculating the limit as n goes to infinity, but we are counting it as a constant as we're summing over I. So here we're summing I equal 1 to something, and we have 32 divided by that something squared. So as far as the summation is concerned, n is a constant. We're just summing I equal 1 to n, and then we're multiplying by 32 divided by n squared. So the 32 divided by n squared can be factored outside of the summation. Not the limit, because as far as the limit's concerned, n's your variable. But as far as the summation is concerned, n is a constant. It doesn't matter that you're right, that your upper limit of integration is being squared and divided here. That doesn't matter. So this n and this n are the same, but it's okay because we're considering I the variable. So we factor the 32 divided by n squared out of the summation. We could choose to factor the 20 divided by n out of this summation and leave a 1 here if we wanted to. I chose not to do that, but we're allowed to do it. And so in the next video, I will finish this limit and we'll arrive at the answer.